An antenna. An antenna is created by wrapping a square frame with side length A by a wire capital N times, and then connecting the leads to a resistor R and a capacitor C as shown in the figure. So square frame wrapped capital N times with a wire connected to a resistor and a capacitor in series. A plane electromagnetic wave with electric field E is equal to E max cosine kz minus omega t in j hat direction propagates in the plus z direction. The origin is at the center of the frame. So you can see here a Cartesian coordinate system is drawn. The origin is at the center of the frame. Part A. What is the magnetic flux through the coil in the direction of the positive x-axis? Hint, the identity sine A plus B plus sine A minus B is equal to 2 sine A cosine B may prove helpful. Okay, now, first of all, we have the electric field E given by E max cosine kz minus omega t in j hat direction. So this is given. The pointing vector, which is going to determine the direction of the plane electromagnetic wave, is given by 1 over mu 0 permeability of free space, electric field cross product with magnetic field, and we're given that this is in k hat direction. Okay. So this is in k hat direction. Now, for this pointing vector to be in k hat direction, we have to determine the direction of the magnetic field. Looking at the relationship between I hat, j hat, and k hat here, I hat cross j hat is k hat, j hat cross k hat is I hat, k hat cross I hat is j hat, etc. So we have to find out which cross product with j hat gives us k hat. So if you look at j hat cross product with I hat, j hat cross product with I hat gives us minus k hat. So what we need is actually j hat cross product with minus I hat, which is going to give us plus k hat direction. So the minus sign goes here. It's going to give us plus k hat direction. So this tells us that the magnetic field must be in minus I hat direction. And what is the magnitude of the magnetic field? Magnetic field is related to the electric field as E divided by C. So it's going to be minus E max divided by the speed of light c cosine kz minus omega t I hat. So this is in minus I hat direction. Okay, now we have to determine the flux. So the magnetic field is in minus I hat direction. So what current creates a magnetic field in minus I hat direction? So using the right-hand rule, I can see that if the current flows in the clockwise direction, 4 fingers of the right hand curl in the direction of the current, the thumb points into the page in minus I hat direction. So this must be the direction of the current that's going to create a magnetic field in that direction. So that's going to determine the direction of my area vector for each coil. All right, so the flux through each coil is basically phi B, magnetic flux, is equal to the integral, because the magnetic field is z dependent, it's the integral from minus a over 2 to plus a over 2, because the origin is at the center of the frame. Dot product of magnetic field with the area vector. Okay, so this is the integral from minus a over 2 to plus a over 2 minus E max divided by C cosine kz minus omega t dot product with the area vector. Now the area vector must be a dz. So let's see, this should be a dz in minus I hat direction. The direction is determined by the right hand rule following the current. So why do I have to consider the area vector as a dz? So magnetic field is z dependent. So if I take an area element for each coil here, for each dz I have a different magnetic field value. So a dz is basically the area element on which the magnetic field is magnitude is a constant. So it's minus a dz. I had the direction of the area vector is determined by the current. It's parallel to the direction of the magnetic field. So this is the direction of the area vector. All right, so this is going to be the dot product of the magnetic field with a dz in minus I hat direction. So the magnetic flux pi b can be written as the integral from z is equal to minus a over 2 to plus a over 2 ae max over c cosine kz minus omega t dz. I hat dot I hat is 1, minus minus becomes plus, so the minus signs cancel. So this should be the integral I need to evaluate to find the magnetic flux. Now, the integral of cosine kz minus omega t dz will give me a 1 over k sine kz minus omega t. So if I perform this integration here, I will find the magnetic flux phi b is equal to a E max divided by C times K sine kz minus omega t, and this is to be evaluated between z is equal to minus a over 2 and plus a over 2. So that's what I have to perform. Now, k times c, k is 2 pi over lambda, so 2 pi over lambda times c is actually the angular frequency. Angular frequency omega is c times k. This is known as the dispersion relation, omega k relationship, dispersion relation. Remember that c is equal to lambda f, k is 2 pi over lambda, so this becomes 2 pi f, which is omega, the angular frequency. So let me just remind myself that omega is equal to ck. All right, so I can write the magnetic flux as ae max AE max divided by omega, the CK product. Now I'm evaluating sine kz minus omega t at plus z is equal to plus a over 2. So this will be sine ka over 2 minus omega t minus sine minus ka over 2 minus omega t. So this will be the flux. Now this can be written as AE max over omega sine Ka over 2 minus omega t. Here I have a minus sine of minus x. Sine of minus x is minus sine x. So this is going to be plus sine Ka over 2 plus omega t. Now, it was mentioned that we should use this trigonometric identity. Sine a plus sine b is 2 sine a plus b over 2 cosine a minus b over 2 in the problem statement. So if I write this sum of two sines, the magnetic flux phi b is going to become AE max over omega sine a plus 2 sine a plus b over 2. So let's see. I have 2 sine a plus b over 2 Ka over 2 minus omega t plus Ka over 2 plus omega t. Omega t's will cancel. I will obtain Ka divided by 2. So sine Ka over 2 cosine a minus b over 2. So cosine Ka over 2 minus K over 2. K over 2's will cancel. Minus omega t minus 2 omega t divided by 2 will give me minus omega t, but cosine is an even function, so that's cosine minus omega t is equal to cosine plus omega t. So the flux can be written this way. So what is this flux? This is basically the flux through, one coil. Okay, so that's the flux through one coil of this antenna. All right, so we have an antenna that is made of a square frame which is wrapped n times with a wire, and the leads are connected to an RC circuit. The wire, the frame will have a self-inductance L. A plane electromagnetic wave propagates in the plus z direction. The electric field is in j hat direction. The propagation direction is k hat. So because j hat cross I hat is minus k hat, j hat cross minus I hat is k hat, the magnetic field must be in minus I hat direction, and we have this relationship between electric field and magnetic field E is equal to BC, that we have obtained using Maxwell's equations. So we can write B as E max over C cosine kz minus omega t, propagating in minus I hat direction. The flux is found by taking the dot product of the magnetic field with the area element dA, integrating from z is equal to minus a over 2 to plus a over 2. So, looking at the direction of the magnetic field B, basically, what current creates that magnetic field? It was my question, and I see that that magnetic field would imply a current flowing in the clockwise direction, and in that case, I would see that the area vector is in minus I hat direction, and that's actually the direction that is given in the schematic drawing of the setup here. So with that, the area vector, the current convention being in this direction, the area vector is in minus I hat direction, and it is a dz, because the magnetic field is constant within the range z to z plus dz. I have to consider a dz as the area element. So I take a dz element here. A times dz is the area. It's pointing in the direction minus I hat, determined by the current convention direction. So if I take the dot product, I obtain AE max over C cosine kz minus omega t dz, integrated between minus a over 2 and plus a over 2. The integral gives me 1 over k sine kz minus omega t. I recognize C times k as being C is equal to lambda f, k is 2 pi over lambda. This is 2 pi f, the angular frequency. Omega is equal to ck is the dispersion relation. And then I evaluate this at the two limits, minus a over 2 and plus a over 2. And using this trigonometric identity, I can write it this way. 2a e max over omega sine ka over 2 cosine omega t. This, what I have just calculated here, is the flux through one coil. So basically, the question was, what is the magnetic flux through the coil? So that's just one coil in the direction of the positive x-axis. This is basically the flux that we find in the direction of the x-axis. AE max over omega 2 sine Ka over 2 cosine omega t. That's the flux through one coil only.